this is Mr. Huff, and let's talk about rockets and calculating the average velocity. Let's consider this diagram on the right. This is a force vector that represents the thrust coming from the engine. This is a force vector that represents the drag acting on the rocket as it flies through the air. Two things you need to pay attention to when designing rockets is CG, the center of gravity, and this is the point of the rocket at which it balances the left side versus the right side, the front versus the back. And then CP is the center of pressure. Think about this as the origin of the thrust. Okay, so those are some things that are interacting. Why this is difficult in the real world. So as you launch a rocket and as it flies through the air, there are a lot of things that are changing. You have air resistance, which is dynamic as you increase velocity. We learned that velocity is a component of drag, so as you increase velocity, it's also causing an increase in your air resistance. Also, the mass of the rocket is changing because the fuel is being burned and turned into gases to produce thrust. So the mass is decreasing, and if you think about the momentum law, as you decrease mass, the velocity is going to increase. So another thing is the forces, your thrust, your drag, your weight, and the acceleration are all dynamic. Throughout the flight, all of those are changing and interacting together. So really the appropriate thing to do is use calculus to understand this, but we want to approach this with a little bit of algebra. In order to do this, we have to make some assumptions. We're going to assume that there is no air resistance. So in a perfect world that had no air, what would this rocket do? And then we're also going to use an average weight of the rocket. So we're just going to add the weight of the rocket and the weight of the engine together, and that's going to be our total weight. Okay, so we're going to use that average weight. So then we're also going to work with other averages, average thrust and average velocity. When we do that, we're kind of looking at the beginning versus the end rather than all the changes in between, and we can use some simple algebra to understand what's happening. We need to understand these two formulas. So we know that weight is equal to mass times the acceleration due to gravity. Therefore, mass is an expression of the weight divided by the acceleration due to gravity. Another thing we need to recognize is that our velocity is dependent on acceleration and time. And therefore, acceleration is your average velocity divided by time. I'm not going to use the subscript here, but this is average velocity, and this is the time that the rocket is accelerating. So we can think about, first I want to talk about thrust up here. Our thrust is a force, and it is the total impulse provided by the engine divided by the time that the engine burns producing thrust, okay? And those are two specified values, usually on a specification table from the rocket engine manufacturer. And from these two values, we can calculate the thrust. And then we can look at Newton's second law, F equals ma. And we can replace F with thrust minus the average weight. So the difference between those is our net force acting on the rocket, and that's equal to the mass times the acceleration. And so now we can look at the other side of that equation, mass times acceleration. We talked about mass being equivalent to the weight divided by the gravity, and our acceleration is the average velocity divided by the burn time. So this is the equation we're working with. We can rearrange that and simplify to find our average velocity by taking the thrust divided by the average weight minus 1, multiply that times the gravitational acceleration times the burn time. This is the formula we're going to be using. Write this down. It's also useful to keep this in mind. V stands for average velocity. It's measured in meters per second. T is your average thrust, measured in newtons. Weight is your average weight, also measured in newtons because it's a force. Be careful not to use the kilograms. You've got to convert it to a weight, okay? And G is your acceleration due to Earth's gravity, and we're going to use this value, 9.81 meters per second square, for all of our calculations. And then T, the lowercase t, is your thrust duration, or another way to say that is the engine burn time. That's going to be in seconds. Let's go through an example problem. Let's say that you have this rocket that you've built, and you're going to put an engine in it that can produce 7.8 newtons of thrust. And the rocket weighs 0.35 newtons. That's roughly 35 grams. Then we convert that into newtons. Anyway, I just rounded that up. So anyway, 0.35 newtons is our weight of our rocket plus its engine. And then the burn time for this engine is half a second. Okay, so this is a pretty small engine. Our unknowns, we're looking for the average velocity in meters per second. Our equation is the one we just talked about here, velocity, thrust, weight, gravitational acceleration, and time. This is our formula written out in a way that you can put it in your calculator. It will look exactly like this if you put it in your calculator. 2 parentheses, 7.8 divided by 0.35, that's your thrust and your weight, minus 1, close that parenthesis, times gravity, times your burn time, and you get 104.41. So for our answer, we're going to use the first 4 numbers because I love 4 significant figures, and we end up with an average velocity of 104.4 meters per second. That is the average velocity of the flight of this rocket using that engine, okay? I hope this helps you, and let me know if you have any questions. Thank you for watching.